I'm Sam Savage, Executive Director of ProbabilityManagement.org, and I'm joined by Joe Scott, the founder of Pyrologics. It sounds like a fireworks company. What's the story?
We're a fire science company. Do wildfire hazard and risk assessment. We've been called a wildfire risk assessment research firm.
Great. Well, we're here to discuss today the difference between wildfire risk and flood risk. And you wouldn't think that we need to discuss this subject, but unfortunately, people often model these things in very similar ways. Here I have a model of a flood, and we're going to simulate various flood levels. So that could happen, or that could happen, or that could happen. And, throughout the boundary between blue and green, we've got the same flood height. So how do people model forest fires? Often like this. They change blue to red. And then, within this boundary, we have a certain probability of a fire. And seriously, I talked to a risk manager at one point who said, yeah, it's like floods. We've got these concentric rings of the chance of fire. Well, so Joe and I are here to tell you that it's not the same as modeling a flood. And when I first heard about this problem, it took me a while to get my head around it. If there's one word, I think, that really differentiates these risks, it's that there is something called spatial correlation in forest fires that you do not have in floods. And so what I'm going to do is build a little tiny model of a forest fire, which is just a minuscule version of the sorts of models that Joe builds, but it's enough to explain the concept. So I have a 5 by 5, square grid of a forest. And the probability of fire, for this simple example, in a given year is 20% in every grid square. The problem is I have to build a power transmission line from the left-hand side of the forest to the right-hand side of the forest. And I need 5 transmission towers. And so I have a number of valid ways I could wire myself across the forest. I'd go straight across. There's pattern 1, pattern 2, pattern 3. Any of these things will get me from the left-hand side of the forest to the right-hand side of the forest. And the way people would often model risk is, okay, what's the expected number of towers that you would lose in a year to forest fire? And, well, every square has a 20% chance of fire. Any tower configuration is going to use 5 squares. 20% of 5 is 1. So no matter what I do, on average, I can expect to lose 1 tower. And then people would walk away from that and say, okay, job done. No. Think of spatial correlation this way, and Joe, correct me if I'm wrong, but you've got things like canyons, wind directions, contiguous pieces of forest that tend to burn together. And if my house floods, my neighbor's house is going to flood. If my house gets burnt down a fire, my neighbor's house might survive just due to the local wind conditions and things. So what I've done here is I've modeled what I call spatial correlation. Now that's a word I do not like to use because that's the kind of word that could trigger, PTSD, that is post-traumatic statistics disorder. But just think of these different colors as being areas of the forest that would tend to burn together. The white ones are independent, okay? But if anything in blue goes, the other ones in blue are more likely to go. If anything in green goes, the other greens are likely to go. If anything in yellow goes, yellow is more likely to go. Now, this has no effect on the average number of towers we burn down, which is 1. But the game is not over with the average, right? That's the flaw of averages. And so, well, what else might you worry about beyond the average? Oh, how about extreme events? For example, if you lose more than 3 towers, a city loses power for a week, right? All the refrigerators, all the hospital equipment. Yeah, well, that's a big deal. But that's not measured by the average. That's measured by the tails. And so I actually have the whole distribution here. What we're going to do is cycle through the various configurations of tower placement. So I'm not talking about mitigating the fire itself. I'm talking about preparing up front for a fire, just to show you there really is a difference. Okay, so pattern 1 goes straight through here, right? And notice this, the chance of exceeding 3 towers burnt down is 1.5%. Now, let me point something out. I haven't played with the trials here, but I've got 10,000 trials, and my simulation trials do reflect this spatial correlation. So trial 2, trial 3. So with every trial, you can see I get a different set of fires down here, right? And then simulating over all those trials, I get a 1.5% chance every year. If I pick this configuration for my transmission line, I get a 1.5% chance of losing 3 or more towers and blacking out the city for a week. Okay, so let's try another configuration. Configuration 2. Configuration 2 went straight through these independent ones, and it picked up a green and a blue. And wow, it dropped to 0.81%. Here, let's go compare that. I mean, if it's your city that's going to be without power, you're going to notice the difference between 1.5% and 0.8%. And you can see how the distribution changes here. So watch that distribution as I cycle through these others, okay? 2.53%. That's running straight across the bottom there. Or 1 up from the bottom. 0.83%. 2.61%. 1.13%. And 0.7%. So if you had blindly gone ahead and said, well, it doesn't matter where I put the poles because on an average I'm going to lose 1 power tower, wrong, because the chance of exceeding 3 of them, I think the high was around 2.6% or something, and now 0.7. I mean, that's close to a quarter of that initial risk. And what this required was a simulation of the fire that preserved the spatial relationships of the squares. So, Joe, I'd like to turn it over to you now and hear what people do in the real world and the sort of technology that you folks have developed in this regard.
That'll be great. I'll share my screen now, and because that's a great introduction to the way that we've been doing this for, it's been about 10 years now, using a modeling system that was developed here in Missoula. So I'm going to talk now about the kind of Monte-Carlo fire simulations that were developed at the Missoula Fire Sciences Lab that do, using fire science, what Sam just showed you in Excel. And to start with, I'm going to show wildfire hazard across California. I'm going to first show you the flaw of averages approach to that, and then but also show you that the modeling that we do inherently does what Sam was just talking about. So we did this project in California, started with the fuelscape there in the center, and then in the next slide you'll see it's important for these different regions of California that we accounted for trends in fire currents over time. We can call this climate adjusted if you want, or fuel load adjusted, but here in group 1 in far northern California, what you can see is a strong trend, strong increase over time in the area burned. Southern California, the south coast, upwards, but not as strong. And then the third group in the Sierra, where there are 2 huge fires this year, still burning right now. Moderate upward trend. When you account for 2020 and 2021, in this data set, it'll be much stronger upward trend. So we accounted for all that. And we produced this map of burn probability. This is a raster. This is just like the 5x5 square that Sam showed that was a 20% chance of burning each square. Well, this is millions of squares across the state of California, and in the legend you can see the probabilities range from less than 1 in 1,000 in the yellow to more than 10% per year, which is quite high, which is this area up here. Now, when we look at this across the whole state, what we can see is an average of approximately 1 million acres per year. That's what that averages out to. That's what this is showing here on this orange outlined circle here is an average of about 1 million acres per year. That used to be 600,000 without doing the climate adjustment. But that's just the average. What we really want to see, oh, actually, let me show you that now this slide shows where the 2020 fires were. And if I were to go back and forth between them, what you would generally see is that, well, those fires were generally burning in the places that our modeling said was high probability. Well, we went to a little bit of effort now to quantify that. And so this is the expected distribution of area burned in each of those classes here in our legend. Expected annual area burned on average. See, this is still on average. And then this is what we happened in 2020. Now, in 2020, it was actually, this is in a relative scale. In 2020, it was 4 times higher than we were expecting, 4 million acres instead of 1 million acres. But when you normalize for that, they were at the very least in the right place. I show you this to give you, so you can have at least a little bit of faith in the modeling that's underneath this. So now when we start answering other questions.
So Joe, let's clarify. So
Sure.
These are showing the relative probabilities based on your map. So in other words, whereas so the blue and the I got it. This is the distribution of the amount of area burned.
Yeah. And so if I let me turn on this guy, the laser pointer. So up in this area, so in the Klamath Mountains, the Trinity, the far northern California, have a much higher burn probabilities. They used to be in Southern California before that climate adjustment, but now we see much higher burn probabilities up there. And so even though one trial, right, there was only 1 year, we simulated 10,000 years, one trial, the year 2020, produced this event set, these gray fires here. Well, what we found is that there was way more area burned in that one trial than we were expecting. I'll show you how that plays out. We have a probability associated with that with 2020. But what we wanted to say was, well, are they at least in the right places? Does our map not accurately, but does it reasonably reflect
Got it.
that? And that included that this very highest probability band that's underneath there now, that greater than 10%, it's a very, very small target of a very high probability. Well, in
Sure.
2020, we actually burned almost exactly the right amount of it, that's really luck, right? Well,
Yeah.
I tell you what, 2021, we're actually burning a little bit more, a little bit higher fraction of that same thing, just to the north of the August complex. We burned a bit more. Okay, so now on the next slide, if I can go forward here, what we see is a fire size distribution, exceedance probabilities of different fire sizes. And this is in log space, final fire size and the exceedance probability. Well, for small fires, the exceedance probability is bigger than 100% or 1, and that becomes how many fires per year might you expect to see. So reading off of this chart, 10,000 acres, that number right there in log space, that's 16 fires per year greater than 10,000 acres, 1.7 fires per year bigger than 100,000 acres. And then we get all the way down, let's see, annual probability of about 1 in 50 of a fire bigger than 1 million acres. So last year, the August complex was about 1 million acres. So we would say that that was essentially a 50-year event by our modeling, which may or may not have, it's a higher prediction than most have done, but it might have underpredict where we're at. So that was on an individual fire basis. This is what a whole fire season across California might look like. This looks like it's linear space, right? So like I said, last year, 4 million acres burned in California, which is right down here on this chart. And that, according to this graph, is a 100-year event. Had a 1% chance of occurring. So this is an exceedance probability curve. The annual probability of exceeding a total area burned in California of our highest event was probably 8.5 million acres in one season. That's probably still a little bit low. But what we can see on here is, like, I think I said, yeah, the average is about 1 million acres. That puts it right here. So there's actually like a 70% chance of burning less than the average number of acres, only a 30% chance of burning more. But if you burn more, you usually burn a lot more. That happened in 2020. It's happening again in 2021. I think we've already burned probably 1.5 million acres in California this year. It's September 1st. Okay. Now I'm going to talk a little bit about a few different applications of this kind of fire modeling. One is sediment load to a reservoir. So Sam talked about impacts to transmission lines. I'm going to talk to impact to communities, reservoirs, and I think one other application. So sediment load to a reservoir. I don't have a very good animation here, but on the left side there, those different colored patches represent different individual wildfires. And those are simulated wildfires that affected this basin. And it's just a 6 code watershed, but let's just say it's a basin that drains to a reservoir. So those are all the ones that impacted at least 1 acre of it. And then the red dots are the start locations of those fires. And we call this area where fires can start and reach some target, we call that the fire shed. So analogous to a watershed. It's the places where fires can start and not quite flow to like water, but spread and reach a certain target. Well, then let's say that each one of these simulated wildfires, and they're all overlapping, there's hundreds there that overlap. Well, each one of those, we can do some analysis and estimate how much sediment it might have produced to the reservoir within this basin. And then for each one of those events, now we can make an exceedance probability curve based on sediment load to that reservoir.
Well,
Here's that curve.
To explain the sediment, Well, are you talking ash or something that gets into the water and then you can't drink the water anymore? What are you really talking about here?
No, it's not ash. It's erosion, right? So when a forest fire burns through, it might burn up the canopy, so rainfall reaches the ground, the soil is exposed, and then that leads to erosion events, and
I
the
get it.
erosion contributes sediment into a reservoir.
So it basically fills up with mud.
Correct. Yeah. It does two things. It increases the turbidity, which is a problem if it's drinking water, and you have to filter that out. But mostly it decreases the capacity of the
Got it.
reservoir system over time.
Got it.
And so this is in linear space, and then the next graph I show, it's in semi-log space. So it's a common logarithms of the impact. The 1 year, this is just in 1 year, what's the sediment load? And then what I'm also showing here is what if it's the hypothetical, what if we did fuel management in and around the basin that serves this reservoir, so that we could reduce the probability of fire and we can reduce the intensity of fire. Both of those reduce the probabilities, these exceedance probabilities. These are actually, these are real simulations from a project that was done in the Sierra Nevada of California. And so I really like these exceedance probability curves, and especially showing some different management alternatives, because it allows me to put it back on the decision maker. And I've heard you say this in the past, Sam. What is the acceptable level of sediment into a reservoir beyond which you can't tolerate it? And so you could say, well, okay, that's 100,000 megagrams we can't tolerate. Well, we know we can say what that annual probability was, and we can see how much we can reduce that. The truth is that nobody seems to know what these thresholds of acceptability are. They may not exist for a lot of things. So another option or another application is community exposure to wildfire. So now we're talking about houses.
Sorry to interrupt you here.
Sure.
But back up to the previous slide for just a sec. So the sediment load really translates to less water, correct?
Correct.
At a time when the value of water seems to be going up, if I'm not mistaken. During droughts,
in a way, yes. Yeah, less storage capacity. And really what it eventually boils down to is eventually a cost. You can avoid the sediment through fuel management and get this, or you can dredge it from the reservoir once it gets put in there at great expense.
Got it. Very good. Okay, good.
Yeah, so there is something you can do about it. It just costs a lot of money.
Yeah, okay, great, great.
Okay, so community exposure to wildfire. This is a community in Idaho, out not too far outside of Yellowstone National Park. And on this figure here, the black dots represent the locations of houses, and the reddish colored dots represent the simulated wildfires that burned at least one house. And they're colored and sized by how many homes they exposed at one time. So the smallest ones are 1 to 100 homes. And then actually in the background, the stippling, those are all fires that didn't impact any homes. So lots of fires here don't get big enough to impact any homes. A few of them can impact a lot, 1,500 to almost 2,200 homes. So a couple of different ways that we look at that risk from an individual structure basis. We often will do this. We'll put them on a scatter plot of probability and intensity. So those two things combined, or what we call hazard, wildfire hazard, the likelihood and intensity are hazard, and then the further up here, the more at risk, the more hazardous the situation is. But as you can probably predict, we can also put that onto an exceedance probability curve for the numbers of structures exposed in any 1 year. So this could be from multiple fires in 1 year, but what we can see from this curve is that there is a 5.4% chance of burning at least one structure. 95% of the fires that start here don't reach any structures. 5% do, and most of those that do don't impact very many structures at all. Looking way out at the tail is roughly a 1 in 10,000 chance of burning at least 2,000 structures. So Sam, you'll see this is perfectly analogous to your spreadsheet view of risk to transmission towers, except this is for houses and it's built from the fire modeling data. And then bringing it back to floods, that we often like to do this and say, well, floods, you hear about a 100-year flood event. And I talked about a 100-year fire event in terms of area burn, but you can also look at it in terms of structures exposed. In this community, a 100-year event, so a 1 in 100 chance of happening annually, was 171 structures. That or more will happen in any given year with a 1 in 100 chance or more. Now, these simulations, I will say, were not climate adjusted. So all of these numbers, don't rely on the absolute numbers here because they're all higher. This whole curve is actually shifting upwards, shifting outwards. And then the last example, actually, this is going on today all over the country and in California, is how we apply these risk assessment concepts to supporting decisions made on wildfire incidents. So there's a separate kind of similar modeling to what we did for the whole state of California, but this is for a wildfire incident, and this one is just for 28 days, right? So we know where the fire is right now, and we say where might it be in 28 days? And we have a lot of different potential outcomes. These are usually done with about 2,000 simulations. 2,000 ways the next 28 days can play out. On the left are some of those different outcomes laid on top of one another. They're not just getting bigger. Some are going in that direction, some are going in this direction. It kind of looks like they're just getting bigger, but that's really not quite the case. And then on the right, you see the burn probability map that we make from that. And this, again, will give you the average outcome if you wanted to look at averages. But really what we like to do is to look again at exceedance probability curves. And this one for fire size. Now, on this one, what I'm showing is a hypothetical example of 2 fires that might be burning in a region in California. And you need to know how to allocate your firefighting resources. These are decisions that are made every day, by the way, at the national level and at the regional level, how to allocate scarce resources. And so looking at this one, we can see the exceedance probabilities for two competing fires. And what I'm showing here is this one called the Lion Fire in the blue on the left. It's going to produce larger fires. That it either started larger. Actually, the fact that the exceedance probability of 1 starts at a higher number, that's because the fire, when I started this analysis, it's already achieved some size. I didn't start it at 0. So it's already achieved some size. But it's fuel, weather, and topography that makes the Lion Fire more prone to getting larger within a 28-day period, and the Basin Fire less likely. But here's the trick. That's just fire size. When you overlay that on what is underneath the fire, whether it's houses, surface drinking water, transmission towers, things that we don't really want to burn up, that they're damaged by fire. So let's call that loss or net value. Well, actually, net value change, because now I'm going to complicate things by saying fire can also convey benefits. And we've been accounting for the beneficial effects of fire for a long time. It's quite challenging. Beneficial effects of fire on wildlife habitat, for example. It can do bad things at some intensities. It can do good things at other intensities, and where these things are. So what you can see now on this graph is that the Basin Fire, even though it was smaller, it was not projected to get quite as large. Because of where it's burning, it's actually projected to produce more negative effects, more adverse effects, because it was small, but it's in a place that can cause a lot of damage. The Lion Fire, in contrast, even though it's getting large, it's actually doing a lot of good where it's generally burning. and the adverse effects that it can produce don't rise to the same level as the basin fire. And so this is the type of information that incident management teams, or actually area command, and there's some risk management assistance teams are looking at information like this when they're trying to allocate resources.
Well, that's quite amazing, because we don't think of wildfires as being good that much. But of course, an obvious way, I guess, they're good is that if they burn up a bunch of fuel, then that fuel load is gone, and it's not going to burn there for a while again, right? I mean, if I have a flood somewhere this year, that doesn't mean we've used up that much water, and so that water won't be available to flood me again next year.
That's right.
Have no effect at all. And in that regard, I suppose by the time we've burnt down the entire state of California, then we'll be okay for a century or so. I don't know. I mean, well, obviously, I do think fire management has a lot more intricacies than flood management in that sense, right?
It very much does. In fact, I think if we were looking at maps right now of some of the fires that are occurring today in California, we'll see some of those effects where fires that have occurred in the last few years, the fires are stopping there. This year's fires are stopping there, or they're allowing the firefighters to stop the fire there. So that's what, it's a very big difference between floods and fires, is that floods are generally independent and wildfires are not. Now, what we're finding though, Sam, in 2021 is that they're not independent, but not for a very long time. The Dixie Fire, for example, in its early days and weeks, burned through large areas that burned within the last 10 to 15 years.
Really?
Yeah. And honestly, we did not expect, that was without big winds. We did not expect it to do that. And that's a very, very strong signal of the drought, and whether that's climate or not, I'll leave to other people. But you can't stop fires no matter what the fuel is. You can't stop fires when it's as dry as it is.